Welcome and welcome back. And this is the next to last, not quite final, the penultimate chapter or episode of Supercomputing Plain English. We're going to be talking about graphics cards, okay? Number crunching in your graphics card. So all the usual disclaimers about it's an experiment and mute yourself and blah, 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 blah. Mute yourself, supercomputingplainenglish@gmail.com. Debbie is carefully monitoring that. Right, so we are here. We're almost, this is the next to last. Okay, and thank you to all the wonderful folks for helping. Okay, and experiment coming. So I cut out what had been the first entry in here because that happened last week. But these other things are coming up and you totally want to sign up for them. And I just found out yesterday that we had a paper accepted at the PERC conference. So that's fun and exciting. Okay, so this is the outline. We'll talk about what general purpose graphic processing units, what that's all about. It's programming. We'll dig a little deeper into stuff and we'll just see how things go. Are we excited? Yes. All right. All right, so what are we talking about when we talk about GPUs? We're talking about accelerators, not the pedal that you step on in your car, but instead we're talking about hardware whose job it is to run stuff real fast, and in particular to run stuff faster than the regular CPUs do. So in the olden days, in the long, long ago, before my long white beard made it all the way down to the floor, and by this I mean the 1980s, and even to some extent in the 1970s, if I remember right, you used to be able to buy for your supercomputer. You couldn't typically buy this for your PC, but you could buy for a supercomputer what they called an array processor. Nowadays, that kind of capability is built into the CPU. So the x86 CPUs do this. I believe the ARM chips do it, the Power chips, the Spark chips, you name it. I believe now pretty much all of the major server CPUs and desktop CPUs have this kind of what we call vector processing in them. But back then you had to buy that as an add-on, and it was sort of a thing you plugged into another thing, and then it could run calculations super fast, where by super fast, I mean ghastly slow compared to even what your cell phone does now. More recently, there's been a lot of activity in what's called field programmable gate arrays, which is where you're very deep down into the hardware and you're sort of reconfiguring the hardware more or less right before you do a run, in principle, even during a run, although that's usually not how they're used. We're not going to talk about that specifically. We're going to talk more about a kind of accelerator that's cheap, and that over the last 10 years or so, they've made relatively straightforward to write code for to do number crunching. So we like accelerators because, surprisingly, they speed things up. On the other hand, the downsides of accelerators, number one, they cost money. Right? You already bought the server or the PC, whatever it is, but now you've got to buy this extra thing that's going to cost you more money. Though, even though they are expensive in the absolute sense, they're often cheaper on a per unit of computing speed sense. Under some circumstances, it can be labor intensive and tricky to write code for them. And depending on the particular way that you're writing code, you might or might not be able to run the same code on other kinds of accelerators or on servers that don't have accelerators. So again, depending on how you do the code, in which case your labor cost, and labor is the biggest cost in computing, right? People, machines, I don't want to say machines are cheap, but on a per unit of processing basis, machines are cheap. People are expensive. So you want to make sure when you're writing code that the labor cost you're investing in writing the code is going to pay off, and especially that whatever you put in is going to last a good long time, that you're not just going to throw away all that labor you put into rewriting your code. So the king of the accelerators today are the GPUs. Now, I actually have a picture here of one that's not technically a GPU, but it shares a lot in common with GPUs, so we'll think of it that way even though it ain't. But so there's the NVIDIA version, here is the AMD version, here's the Intel version, right? And these are all, I guess, the latest versions of the latest versions. Now, you remember this one. We've seen this picture a couple of times. This is the progression of 1 trillion calculations per second, or a teraflop, from 1997, when it was hundreds of millions of dollars and filled up an entire data center, through 2002. This was the one we had here at OU. It took up a row, I think it was 11 racks, and it cost under $1 million. By Christmas of 2012, any of those 3 vendors would cheerfully sell you a card that would do 1 trillion calculations per second that you could pop into a workstation or a server. And now you can actually buy a chip that will do 1 trillion calculations per second. So that's pretty exciting. Over the course of 20 years, we went from a room, and let's call it, what would this be, 9 figures, to a chip. These ones I think are 4 figures, but it'll be 3 figures soon enough. That's a pretty good progression of improvement. Okay. So why GPUs? Well, GPU stands for Graphics Processing Unit. Not surprisingly, GPUs were designed to do graphics. They were not originally designed to do number crunching. But the wonderful thing about computer graphics, about rendering, making pictures out of data, is that computer graphics consists of a lot of number crunching. So the people who were creating these GPUs, they happened to create these beautiful number crunching engines that number crunch very, very fast. They're very rapid to do things like make pictures. Because of course, if we want live photorealistic rendering, we're talking about doing millions or tens of millions, maybe even hundreds of millions of shapes, of particularly polygons, being processed per second to get to something like 30 frames per second on our video games. So they're super popular, and when they're super popular, that means that they can be pretty inexpensive. I don't want to say cheap, that comes with all kinds of baggage, but let's say inexpensive. And the reason they're inexpensive is quite simple. I actually have a slide on this later, but I don't remember when, so I'll go ahead and talk about it now. So here's the problem. It costs hundreds of millions of dollars to design any particular one of these, and the factory where they make them costs billions. I actually had this conversation with an Intel person, gosh, it's got to be 5 or 6 years ago now. And I said, so what does it cost to build the factory? He said, oh, well into the billions of dollars. I think the number was somewhere around 5 billion or something just to build the factory to make the chips. And I said, so I thought I heard it was something like $1 a chip once they start rolling off the assembly line. And he said, I think it's less than a penny. Less than a penny per chip, which means that the cost of making any particular technology is almost entirely the fixed cost of doing it at all. The per unit cost is essentially zero. So in order for you to be able to sell something cheap, all you have to have is a guarantee that you're going to sell a lot of them. So if it costs, well, let's simplify this. Let's say it costs $1 billion to build the factory, right? And you're going to pump out a bunch of chips from there, essentially free per chip. How many chips do you need to sell to charge a mere $1,000 per chip and break even? If it's $1 billion to build the factory. Jim, do you know? 1 million chips. How about to sell it for $100?
No, 100 million. No, you said free.
Yeah, so $1 billion divided by 100 million, wait, $1 billion divided by 100 gives me 10 million. So if you know you're going to sell 10 million chips, you only have to charge $100. If you know you're going to sell 100 million chips, you only have to charge $10. If you know you're going to sell 1 billion chips, you only have to charge $1 a chip to break even, right? If you sell it for $2 a chip, you've just made $1 billion, right? But you got to know that you're going to sell a large number of units, right? So this is the trick with GPUs. They're selling a zillion of these anyway. The computer gamers are willing to pay at least hundreds of dollars for a groovy graphics processor. Some of them, not all of them by any means, but some of them are willing to pay a few thousand. So you can sell a lot of really high quality, super fast GPUs at a shockingly low price because you're selling so many of them, right? Okay. Oh, yeah, so I do have it. See, I told you I had a slide with this. This one, I just picked this up a couple of days ago, this number. I looked it up on the web. So NVIDIA, one of the companies that makes these GPUs, they sold $5.7 billion worth of GPUs in calendar 2017, and that was 80% of their revenue. Okay? So even though the fixed costs may be enormous, they sell so much of it that they're able to recoup those costs and make a profit, right? And rendering images is arithmetic. It's floating point arithmetic, right? We love floating point arithmetic. Now, it turns out that rendering images usually is single precision floating point, or even half precision floating point. So normally floating point single precision, that's typically 32 bits. Double precision is 64 bits per value. Half precision would be 16 bits, right? And Jim generously put some time in to find us some interesting information about that time permitting we'll get to at the end, right? But in any case, floating point arithmetic, that's what people want to do in supercomputing, right? Some people want to do integer arithmetic. It does that too, but floating point is usually the big deal. Okay. So a long time ago, in the 1990s, when the very first model of PlayStation came out from Sony, and it came with, I think it was 100 megabit Ethernet, and the chip inside it was quite powerful. There were some folks at one of the big national supercomputing centers who did a little project where they bought, I don't know, 20 or 30 of these things. And right, they were 3 figures a piece, so this was not a huge investment. And they built a little cluster supercomputer out of PlayStations. And it worked great, except that writing code to run on it was really hard because, and we'll talk about this more toward the end, the way that you write code to run on a GPU, or this was true 10 or more years ago, the way you used to write code, is you had to convert that code into little 4x4 matrix operations. And if you can convert the calculations you wanted to do into a collection of 4x4 matrix calculations, then you could do pretty well on the GPU, on the rendering hardware. But if you couldn't represent it that way, then you would get, well, no speed up, and it'd be a complete waste of time and money, right? And in fact, really the way you'd have to do this is you'd have to use essentially OpenGL or DirectX, one of these standards for writing graphics, for writing rendering, in order to do your number crunching. And this is, of course, a very unnatural way to write number crunching code, so nobody really wanted to do it. Okay. And so I said all that. Okay. So more recently, really in the last 10 years, the people who make GPUs and other accelerators have come to understand that well, heck, we're generating a bunch of these, and they do number crunching really well. We should sell them to people who want to do number crunching in addition to people who want to do graphics rendering, okay? Because after all, we've already paid for the factory. The more units we can pump out, the more profit we will make. The factory is a fixed cost, okay? And so they started creating ways to express number crunching more naturally. I don't want to say perfectly naturally, but more naturally, so that people would buy the cards and use them for number crunching. And this has been, in fact, a pretty big success. Okay? Now, I mentioned that the Intel version of this is not actually a graphics card. It's known as the Xeon Phi, or the mic there is many integrated core. So, you know, we have multi-core. Many core is whatever multi-core is times 4 or 8, right? That's a lot of cores. Right? So many core cards. So it's structured similarly to a graphics card, but it's not focused on doing graphics. And this particular accelerator is based on the standard x86 chip family, but it's based on the version that you find, for example, in lower end laptops and some higher end tablets and so on. So it's a lower end chip because then it's going to draw less power, but then they souped it up. They added some more features to that chip family to make it more number crunching. Okay? So they're currently on the 7200 series called Knight's Landing. The Knight's Landing, so its predecessor, Knight's Corner, it was called, came in only a card version. Knight's Landing currently only comes in a chip version, so you actually have to buy a server with that chip in it, and that's a single socket server, so you only put one of them in the box. But that chip has the various models between 64 and 72 x86 cores, and each one of those cores can do the very high-end vector math calculations that the highest-end chips that Intel and AMD make are currently able to do. So very long vector lengths, which normally you would not get in that family of CPU chips. So these things are capable of doing, each core is capable of doing 32 calculations per clock cycle per core. Okay, that's a lot of calculations. So the various cards they have go up to almost 3.5 trillion calculations per second, almost 3.5 teraflops per card. So a card this big, 3.5 times the computing capacity of the first cluster supercomputer we had here at OU back in 2002. Okay, in a card. Okay. And the internal RAM inside the card can do 400 gigabytes per second. Okay. So pretty fast. Right? All right. So how do we program these things? There are some proprietary ways to do it. There are also some open standard ways to do it. NVIDIA developed their own proprietary way, and we're going to dig into these a little bit more in a bit here. CUDA, and I'll talk about where that name came from. Open Computing Language, or OpenCL, OpenACC, for Accelerator, of course. OpenMP, the more recent versions of OpenMP 4.0 and 4.5 include directives to help work with accelerators. So what we typically see is that NVIDIA and AMD accelerators, you can program in OpenACC. Intel Xeon Phi or Intel Mike, you can program in OpenMP. Both of them, or all of them, you can do in OpenCL. That also applies to things like CPUs, makes the code very portable. And then only NVIDIA can do CUDA because that's proprietary to NVIDIA, which I just said, right? So it was originally called Compute Unified Device Architecture. And it originally actually only had single precision floating point because that's what people use to do a lot of graphics rendering. They later added in initially a little bit of double precision floating point, now quite a bit. And it's essentially a bunch of extensions to C. And they later added Fortran as well, because C and Fortran are kind of the favorite languages for number crunching. To allow people to take the hardware that's in there and use it to do really amazing number crunching. So it's a modest set of extensions, but it requires substantial rewriting of your code. Portland Group was the compiler company that developed a Fortran implementation of CUDA. NVIDIA originally only released a C implementation because their assumption was that most people know C and very few people know CUDA, Fortran. And then later PGI got bought by NVIDIA, so now it's part of NVIDIA. Okay. So, and many institutions support Portland Group compilers among other compiler families. So here's kind of an example of this. So this is just, I'm going to take this array and I'm going to square all the values in the array, right? And this is a little weird. Normally what we would expect to see in a case like this is we'd expect to see a loop, like a for loop, and around the for loop, or inside the for loop would be the calculation that's going to get done in parallel. Right? That's what we would expect, for example, to see in an OpenMP code. But in CUDA, what you do instead is you express what happens at a particular index in the array, not what happens over the many indices of the array. You just say what happens at a specific location in the array, at one place in the array. Okay? And then you have to move the data in and out of the card. So this is the real bottleneck, quite literally. So the card is going to sit in a slot. It's called a PCIe slot. Don't ask about that. But it sits in the slot, and data to move in and out of the card has to go through that slot. And that slot is much, much slower than the speed of the RAM in the server that it's sitting in, and even more, much, much slower than the speed of the RAM inside the card itself. So the bottleneck is moving data in and out of the card. And the goal is have everything in the card, do all the number crunching there, and then only bring stuff out either to do, for example, MPI communication or to write it to disk. Excuse me. Okay. So here's kind of a version of that for our little, what we called our little kernel. Kernel just means a small amount of code that does massive number crunching. Okay. All right. So this says, allocate me an array that lives in the server RAM. And then this says, allocate me another array that lives inside the card. So the H and the D here, by the way, I just copied and pasted this from a wonderful web page somewhere. I think I have the URL there. Yeah. Okay. So the H means host. Host is the server that hosts the card. And then D is device, the card itself. Okay. So allocate the array in both places, right? And then we're just going to fill up the host side array with whatever junk, right? Doesn't really matter what's in there. We're just demonstrating how this works. Then we copy from the host side, from the server RAM, into the card RAM. Okay? Once it's in the card RAM, we do a little bit of magic special sauce, and then we invoke that routine from the previous page. Okay? And this part means do it over the entire array, but broken up into the right set of pieces for the hardware that we have. Okay? Again, I'm hand waving at this. I'm not going to go into a lot of details. Okay? And then when we're done, copy it back out into the memory of the server. And then we can print it out or whatever. Right? Okay. So now, of course, real calculation is going to be way more interesting than that, but that gives you the flavor. All right, so the next thing, so that CUDA is, number one, only available on NVIDIA, and number two, owned by NVIDIA. It's completely proprietary, right? So there isn't like an international standards body for CUDA. It's a purely NVIDIA thing. Now, Open Computing Language, OpenCL, on the other hand, is an open standard. There's a group that runs it called the Kronos Group. You can go to their website. You can look up the OpenCL stuff. They do some other stuff as well. And in some ways, this was meant to be morally equivalent to OpenGL, the Open Graphics language. And it goes all the way back to Christmas of 2008. So they've been through a number of versions since then. The most recent version was released about a year ago, version 2.2. And any company can create its own implementation of OpenCL. So they have their hardware. They just know, so the OpenCL standard says what all the names of the routines are, what their lists of arguments are, and how they're supposed to behave. And anyone can create their own implementation, just like with MPI or OpenMP or what have you. Okay. The difficulty with OpenCL is that just about anything you want to do takes a lot of setup. And some of the things that you might want to do, you're putting a trivial amount of calculation for an enormous amount of coding. If you want to do something super sophisticated and common, then there's probably already routines written that somebody else has taken care of. And this particular example is going to do a fast Fourier transform. An enormous amount of number crunching. But you can see there's a whole bunch of this setup that has to get done before anything interesting can happen. And we go through all this stuff, we do all this machinations here, right? And okay, we do this. And again, I stole this from somebody's webpage. And finally, we get to the stuff that really does the work. It's very exciting stuff, okay? It does all this work. And then finally, over here, deep into the thing, we finally do the FFT, the fast Fourier transform. Okay? So there's all this setup and tear down that has to get done in order to be able to do, in this case, it's a fairly sophisticated calculation, but it's all the setup and tear down that's quite cumbersome. So I think to date in our center, we've had one or maybe two, I think one person ask to be able to do OpenCL programming. And we do, as it turns out, have the ability to support that. So it's no big deal. But one person out of hundreds and hundreds of users who's ever asked to do this. And I don't think it was his code either. I think he was running somebody else's OpenCL code. He was not, I don't think he was doing OpenCL programming. Now, on the other hand, OpenACC or OpenACC, I think it's officially said OpenACC, but I like saying OpenACC. OpenACC is another open standard. It's again in Fortran and C. This seems to be a common theme. Structurally, it's similar to OpenMP. So if you remember back to week 6, chapter 5, when we did shared memory multi-threading, and we did a little bit of OpenMP, and the idea was you would have stuff in your code that if your compiler knew OpenMP, then it would do the parallelization magically for you, and you didn't have to worry. But if the compiler didn't know OpenMP, or if it did, but you had that feature turned off, which on most compilers it's turned off by default, then it would ignore all those directives and it would just compile your code as if it was regular old code, not parallel. So the same idea applies with OpenACC. You write the code, you may have to massage it a bit to get it into a form that's friendly for the accelerator. But if you want to run it on a regular CPU, you just recompile it with OpenACC turned off. Okay? And if your compiler just doesn't recognize OpenACC, you can still compile the code perfectly well. It just won't run in the accelerator. Okay? So what the OpenACC directives do is they essentially say to the compiler, this part of the code should be run inside the card, and here's some details of how that should happen. Okay? Right. And the parts of the code that don't have OpenACC in them, they are the directives. They are going to run on the server on the regular old CPU, not in the accelerator. Okay. So these were developed by several different companies working together. It's lovely when companies work together. So PGI, their compiler supports OpenACC. Cray has a compiler that's only for Cray hardware, and then there's some less commonly used ones and some experimental ones and so on. So you can look all that stuff up if that's of interest to you. So here's a little example. Again, I stole this. Okay. So this is again, the kernel, the number crunching bit that's going to run inside the device, inside the accelerator, the GPU or what have you. Okay. So this is vector add to run in a GPU. Okay. So here's an array, here's an array. Here's an array. We've got 3 arrays, right? So it's R of I is assigned A of I plus B of I, right? And then how many there are. Okay. So this should look super familiar, right? We've all done this, right? We loop over a set of arrays and we do some little operation on it. That's an old friend. But what makes it interesting is this pragma here, this directive that says, first, I am an OpenACC thing. And this is a kernel. So this is number crunching that we're going to be doing. And in the context of accelerators, the kernel typically is what runs inside the device, the accelerator. And make this a parallel loop that runs inside the device. And A and B arrays, they're going to be incoming into the device. And R is going to come out of the device, right? It's going to get calculated inside the device, and then we'll get it later. Okay, or perhaps right away. Right, that's it. That's all we have to say. And then magically, all this stuff happens super fast. Now, the trade-off. So if I was running, for example, on an NVIDIA GPU, the trade-off, the risk I'm taking by using OpenACC is that I might move too much data in and out of the card. And remember, moving data in and out of the card is super expensive, right? So our goal is to do as little of it as possible. So we might not in real life choose to do things this way. In real life, we might put more and more of the code inside the accelerator, inside the GPU or what have you, so that we could avoid moving data in and out. But aside from that, so here's how we write the code, right? And by the way, remember, if the compiler does not understand OpenACC, then it's just going to ignore this directive, and it'll go on its merry way and just compile this the usual way, right? But if the compiler knows OpenACC, then it's going to do all of the magic associated with moving data into the card, doing the number crunching in the card, and then moving the result back out of the card, or whatever the accelerator is. Okay. So all of this stuff is all very vanilla and normal, right? And the only thing that's interesting here is the call to vec add GPU. And in fact, that call is not even very interesting. Notice it just looks normal, right? The only thing that's abnormal about that is that in real life, we might just put the code there, right? It's just a for loop. We might stick the code there instead of calling a routine to do it. But because we want that stuff to happen inside the card, we sort of isolated it into a routine. Now, we didn't have to do that, right? We could have just put all of this stuff in the code where we're currently calling that routine. We didn't have to do it that way. We could have just stuck it in. Okay. All right, so the same thing in Fortran for those of you. By the way, how many of you are Fortran people? Okay, so here's the same idea in Fortran. Now in Fortran, the exclamation point at the beginning of the line means I am a comment. Actually, an exclamation point anywhere in the line means from here on, it's a comment. And if this were OpenMP, it would be exclamation $OMP. But because it's OpenACC, it's exclamation $ACC. Same idea. Okay. And then otherwise, the directive is the same as what we saw in C. Right? So everything is basically the same, just expressed in a Fortran way. Okay. So now, OpenMP. So starting with OpenMP 4.0 and continuing on into 4.5, which is the current fully released standard. I imagine that means they're working on 5.0, but don't quote me. There are accelerator directives and there are vectorization directives in OpenMP. And so the Intel Mic or Xeon Phi accelerators, the card from the previous generation or the chips from the current generation, this is the way to express do stuff in the card fast. And so here's kind of a picture of that. Really, we're just adding in some stuff that says, do this inside the card, right? This particular routine. And then here's regular old OpenMP directive, do this do loop in parallel, right? This is our old friend, matrix multiply, by the way. Old friend. Okay. So straightforward to express, right? You have a little bit of special sauce up at the top of the routine, and then the regular OpenMP stuff in the middle to show the parallelism. And that sort of is the normal way to express parallelism in one of these Intel accelerators. Now, here is, I think, the real difficulty we're facing in the accelerator world. For want of a better analogy, VHS versus Betamax. Does that resonate for people who are not as old as I am? No, not at all. Okay, you've got that. I don't know what the heck you're talking about. Okay, Blu-ray versus HD DVD. No, nothing? Okay, even that. Okay, clearly I'm getting old. I don't know what the current one would be. Is there a current one? So two different standards competing for the marketplace's attention. And one of the things that's holding back embracing the technology is everybody's worried about picking the wrong one, right? So if way back in the 1970s, you bought a stack full, a shelf full, a room full of Betamax videotapes, well, within a year or two, you suddenly had wasted all that money because the Betamax standard went the way of the dodo, and all that was left was VHS. And so pretty soon you couldn't buy a Betamax VCR, you couldn't buy a Betamax player, recorder, and you were stuck with a bunch of movies that you paid a lot of money for that were no good because you couldn't watch them anymore, right? So everybody was really hesitant until Betamax ended up not being the winner. Everybody was very hesitant to invest a lot of money in tapes, right? But once VHS became the clear leader and Betamax faded away, then people bought a zillion VHS tapes. Of course, then we went through that again, not so much with DVD because there was only the one standard, but with high definition video discs. So there was HD DVD, which came with red covers, and there was Blu-ray, which not surprisingly came with blue covers. And everybody was hesitant to jump both feet into the marketplace on that until they knew how that was going to play out. And eventually HD DVD faded away. So now you can't buy the red ones anymore, but you can buy the blue ones at any store, right? So this same problem, I think, is still an issue in the accelerator world. Yes, you can do OpenCL, and that'll work for any platform. But the difficulty is that it's cumbersome to write the code, so most people don't program in OpenCL. On the other hand, you can pick one of the accelerators, you can pick NVIDIA, and you can do everything in native CUDA. But then that code will definitely not run anywhere but NVIDIA. Or you can try and pick, do I pick OpenACC, or do I pick OpenMP, or do I put both in my code and hope I can tease that out when I'm debugging? There's no good answer today because there is no market winner yet. Okay, so we'll dig a little deeper. And by the way, how are we doing on time, Debbie?
It is 1:06. So you're good.
I'm doing good. Okay. All right. So I'm going to dig specifically into the high-end NVIDIA number crunching card. Okay. And there's a picture of it. But the reason I want to do this is called the Tesla V100. The reason I want to do this is I want to kind of do a thought experiment about where we are in terms of our ability to do an enormous amount of number crunching, and how do accelerators really compare to the traditional CPUs. Okay. So I'm not going to spend all day on all the specs of this, but the interesting number on the current card, one of those cards can do 7 trillion calculations per second. So that row that cost less than $1 million, but not a lot less than $1 million, back in 2002, now you can put 7 of those in a single card. Okay. That's a lot of computing capacity. That's double precision. Okay. Single precision is twice that much. Right? So you can do twice as many calculations because they take up half as much space. Right? But now they have this weird thing, half precision. So double precision is 64 bits per floating point value. Single precision is 32 bits per floating point value. So double precision, very popular in applications like chemistry, for example. Single precision, very popular in applications like weather forecasting. But then they have this half precision, 16-bit floating point numbers. So 2 to the 16th is not a very big number. 2 to the 16th, that's 65,000 roughly, right? There's only 65,000 different values that you can store in a 16-bit number. That is not very many. Okay, so interesting. But look how fast it is. It's like 9 times as fast as the single precision, like 17, 18 times as fast as the double precision. Did I get that right? 16 times as fast. Look at this, right? 4, 128, 2, 3, 6, 5, 12, yeah. 8 times as fast, excuse me. 8 times as fast as single precision, 16 times as fast as double precision. Wow. Okay. That's pretty amazing. So you're talking about 100 trillion calculations per card, isn't that amazing? Per card, and that's this super low precision calculations. Okay? Now inside the card you get 16 gig of RAM, and that RAM is super fast, right? 4.5 times as fast as the RAM in your server. Right? So that's awesome. And it's quite a bit of it, right? 16 gig, that's not bad. That's a lot of RAM, and it's super fast RAM. Okay. Now, you do have to have a server to plug it in, right? You plug it into the PCIe slot. Although now, actually, they have a version of this card that plugs into a much faster slot. I'm not going to go into the details of it. But this one that we're looking at, you got to plug it into a PCIe slot. So you're still worried about moving data in and out of the card. That's still a big deal. All right, so let's look at the fastest x86 chip you can buy in terms of calculation speed, right, versus this V100 card, right? So how fast will this go? Well, if you've got a server with 2 sockets to put the CPU chips in, you can do 3 trillion calculations per second in a single server, right? That's pretty amazing, a single server. So each of the chips is doing 1.5 trillion calculations, one chip doing 50% more calculations than a whole room back in 2000, sorry, a whole row back in 2002. But on the other hand, look what you can do. So now you've got a server which has dual chips, but it also has 2 of these cards, right? You can do 14 trillion calculations per second in that server with 2 of those cards in it. So that's 4.5 times faster. But wait, there's more. Okay. So, and by the way, single precision, you just double both sides, so the ratio stays the same. You don't have half precision available in the CPU chips as a general rule. But look at this, 224 trillion calculations per second. If half precision will get your work done, which we're going to get to in a minute. Okay. So the RAM bandwidth now inside my server, 200 gigabytes per second, but these 2 cards collectively will do 1,800, 1.8 terabytes per second. Wow. Again, terrible speed going over the slot that you plug the card into, but once the data is inside the card, 1.8 terabytes per second, right? 9 times as fast. But on the other hand, those cards are only going to get 32 gigabytes per second moving data in and out of the card. All right, and then how much power and heat? Server, I calculated this out for a particular server with particular specs and came up with, I think it was 405 watts per server. If you stick the 2 cards in there, then that goes up by another 500 watts. So you're looking at 900 watts per server. And then is the code portable? Well, if you write it for CPU, it's very portable. If you use OpenACC or OpenCL for the NVIDIA cards, then the code is portable to other cards and actually, and to CPUs as well. Okay. All right, now here's where it gets interesting. Okay. You can tell I like this sort of stuff because I went to all this trouble to figure this out. Yeah, this was how I spent my evening yesterday. Okay. So how many billions of calculations per second do I get per watt of power? Why is that important? Well, because one of the problems that we're having now is that it takes so much power to run a supercomputer that it becomes impractical to have the supercomputer because you can't deliver that much power. Gosh, it's already about 10 or 11 years ago. I was at a meeting where someone said, only half jokingly, 10 years from now, half the power in the United States will be consumed by 10 data centers. Now, that's not literally true, but that's the trend. More and more power is going into doing number crunching in big data centers. Okay? So the amount of calculation you can get per unit of power is more and more a big deal. All right, so if you've just got a server with a couple of high-end chips in it, you're only getting about 7.5 billion calculations per watt. But if you've got that server and you put a couple of accelerator cards in it, you roughly double that, right? That's pretty intense. Same thing with the single precision, it's not very interesting. But even more interesting is, what if you have a rack full of this stuff, right? So I did a calculation on that. 19 trillion calculations per second per square foot of floor space, or 44 if I've got the accelerator. So not quite 2.5 times as much. But then this is where it gets interesting. It's now a good number of years ago, I think more than a decade now, that there's been supercomputers at the very high end of the world's fastest supercomputers that can do a quadrillion calculations per second. So a trillion calculations per second, teraflops. Quadrillion calculations per second, petaflops. Okay. So what does it take to do a quadrillion calculations per second? Well, with the dual socket stuff, and I'll only look at double precision. I threw in the single precision, it's not that interesting. So the double precision stuff, which is usually how this is measured, 9 racks of servers will get me a full quadrillion calculations per second. But on the accelerator side, 4 racks, less than half, to get a quadrillion calculations per second. Now, the real reason this is a big deal is that there's a race on now to be the very first quintillion calculation per second supercomputer. So that's what we call an exaflop. Yes, they really have words for all these things. After exa comes zeta. After zeta comes yada. You know, you'd think they'd do it the other way around. By the way, all those 10 minutes, 5 minutes, 15 minutes. Okay. I think I'll be able to finish in time because I don't want to go into the really detailed part. But all of this stuff, right? What we're trying to do is build machines that can go faster and faster because at every level we identify new problems that we want to be able to solve that we can't solve with our current supercomputers because they're not big enough and they're not fast enough. So we want to get to the next level. So the goal is to get to the next level roughly 2020, 2021, somewhere around there. You know, the US and Japan and Europe and China and probably rattle off Russia, a couple other countries are all trying to be the first. It's like being the first to land a person on the moon, right? They want to be the first country to do a quintillion calculations per second, to be able to have an exaflop supercomputer. Well, if you can do a petaflop in 4 racks, that tells you that you can do an exaflop in 4,000 racks. Now, that sounds like a lot. And it is because each of those racks has on the order of 20 servers in it. So that 4,000 racks, that's 80,000 servers, give or take, right? Somewhere around there. 80,000 servers sounds like a lot, and it is. But it's not ridiculously a lot. Right? There are already supercomputers that are tens and in fact multiple tens of thousands of servers. So what are the downsides? Right? We love the idea that accelerators get us super fast, but you got to rewrite your code, right? The code, you can't just take the old code. Well, okay, you can, but it's not necessarily a good idea. Now, for NVIDIA, for example, you literally can't just take the old code and recompile it and it magically runs inside the accelerator. You've got to do some programming. For the Intel stuff, you can literally take the old code and recompile it and run it inside the accelerator. The problem is it'll run slower. And the reason it'll run slower if you don't do anything to the code is because the individual cores inside the accelerator are individually slower than the cores that you have in your CPU. It's just there are a lot of them. Like more than twice as many as in your CPU. And the result of that is that if you rewrite the code to take advantage of that, then you end up with code that is significantly faster. On top of which, and this is a fascinating property of the Intel accelerators, if you rewrite the code to get really good performance in the Intel Xeon Phi, the mic cards, you rewrite the code to get good performance there. The amazing thing about your code is then you can pull the code back out of the accelerator and run it on the CPUs, and it'll get typically a similar speed up on the CPU. I mean, per core, obviously, but it turns out that what you do to make your code run faster in the Intel cards is what you do to make your code run faster in the regular x86 CPU chip. Which maybe shouldn't surprise us that much because that's what's inside the Intel accelerators, right? Okay, but so you've got to rewrite your code to get good value out of this amazing gear. And we're still, again, stuck in that Betamax versus VHS thing where it's hard to say what is the best way to rewrite your code to maximize the value that you're going to get out of that labor. Because you want that labor to pay off for a good long time. If you're going to put in one programmer year, and a programmer year is going to be well into 6 figures, right? If you're going to invest a programmer year in rewriting the code to run in the accelerators, you don't want to only get 2 years worth of life out of that investment. You want to get 10 or 20 years worth of life out of that investment. And that's currently the big problem. Now, here at OU, we actually did an experiment about this about 5 years ago, where we talked to people who we knew were running code that we knew had been ported to some of the accelerators. I think at that time more NVIDIA than Intel, but I don't know that that matters that much. And we said, we want to work with you to see whether if you use the accelerator features of this code, that the people who write the code, because it was not their code, it was somebody else's, right? It was community code or what have you. We want to see if that's going to get you better performance, and you can use these accelerators. And then in future, we can buy more accelerators, buy more graphics cards, whatever it is. And in general, we'll get way more bang for our buck, right? So we did this experiment. Again, this is about 5 years ago. And it was a failure. And in a very interesting way, what happened was, for a number of the codes that we wanted to help people use, it turned out that only part of the code could take advantage of the accelerators. And the researchers wanted to use the science features that hadn't been ported over yet. So there wasn't a win for them to use the cards. So we want to do that same experiment now, especially because we're gearing up to design our next supercomputer. We want to do that same experiment now because, 5 years have passed. Surely more of the code has been ported into the accelerators. So we don't know yet what's going to come from that experiment. We suspect that once we see what people can do when they're using those cards, there will be support for spending a higher percentage of our total budget on cards than we have done in the past. But possibly not. It might turn out, again, that we only spend a very small fraction of our budget on these cards. Okay. So I think I've mentioned this already, right? And these are numbers, but numbers are not important. The idea is important. What you want to do when you're using the accelerators is at the beginning of the code, just move everything that needs to be in the card into the card. Then do everything, or at least as much as humanly possible, inside the card, not moving it between the server RAM and the card RAM. Keep it inside the card and only bring out of the card the messages you want to pass over MPI, if you're using MPI, and the stuff you want to dump to disk. Leave everything else in the card. Do all the work in the card as much as humanly possible, because the time cost of moving data in and out of the card is unreal. It's huge. Okay. All right. Now I want to talk about machine learning. So we talked about this bizarre thing of half precision, 16-bit floating point numbers, which for normal human beings sounds insane, right? What a terrible idea. You can only store 65,000 different numbers, and yet there are not only infinitely many real numbers, there are infinitely many real numbers between any two real numbers, right? Between 0 and 0.00000000000000001, there are infinitely many real numbers, right? So almost every real number that you can represent, you can only represent approximately, right? You can't exactly represent. And so 5,000 of them, as opposed to 4 billion of them. That's a very approximate approximation, right? So who on earth would want that? Well, it turns out that machine learning, which is a bigger and bigger and bigger deal, it turns out that machine learning is reasonably happy with half precision, 16-bit floating point. So machine learning is part of AI, artificial intelligence. I always, in the context of AI, I always like to put all of the human-sounding things in scare quotes, because I don't really believe that that's what's actually happening. Like, you remember way back in the very first one, I said that the CPU was the brain of the computer, and I put brain in scare quotes. Same idea with learning, which thanks to Jim, because Jim wrote all the text of this. I did very minor edits on it. But Jim did a very good job of catching all of the artificial intelligence We can have a philosophical discussion of whether artificial intelligence is actual intelligence, but it's not. Right? Okay. So the idea is you train the algorithm on a set of training data, and then you throw, let's call it real data at the algorithm, and it's supposed to have learned, again, I'm using scare quotes quite liberally here, it's supposed to have learned what to do with that data based on the training data. Okay. So you need lots and lots of data. There has to be some kind of pattern in there because machine learning is intended to find patterns. And if it's easy for people to find those patterns, it's pointless to do it as machine learning. But if there's so much data, when there's a ton of data, it's very hard. Yes, 5 minutes? Okay, great, thanks. Okay. But if you've got a ton of data, you've got patterns in the data, and it's hard for people to see the patterns in the data, that's a really great application for machine learning. Okay. So I think we've kind of covered those first two, right? Structured learning component. So the machine learning algorithm is trying to find the pattern. It's doing it by doing a ton of calculations. Much of it, in many of the machine learning methods, these are floating point calculations. And it's trying to figure out what the real relationship is between the inputs and the outputs, so to speak. Okay? And the relationship that it's trying to find is typically not something that could be expressed trivially in closed form, right? You can only express it in some sense in an empirical way. Okay? So the machine learning does not give you the exact relationship between the various things in the data, but it gives you a reasonable approximation of that. It's an estimate to predict for future inputs what are the relationships going to be. Okay? So it's not perfect, but it's not bad, and it's getting more and more popular. By the way, good rule of thumb, everything we have computers do is wrong all the time, right? And that's okay. It doesn't have to be right. It just has to be useful. Okay. So it turns out that because you're looking for the trends, it's okay if your answers are not particularly precise. Because you've got so much stuff you're doing that a lot of imprecise data is still going to get the trend going in the right way and will get you close enough to the right answer cheaply, right? The less data, the less accurate, the faster it goes, right? You can always get the wrong answer faster. Okay. So because half precision makes things go faster, you're moving less data between the RAM and the CPU, the calculations take less time because there's fewer bits to calculate, you speed up the whole thing, right? Now, I mentioned earlier that rendering, turning data into pictures, is a lot of little 4x4 matrix calculations. It turns out that some machine learning approaches can do a lot of their number crunching in little 4x4 matrix calculations in half precision, 16-bit precision, which is what some graphics cards love to do. So now you can really take advantage of the hardware that they already went to the trouble of putting in there for the benefit of the people who are playing video games. Okay, so and the reason we like 4x4 matrices in rendering is because there are three operations that we worry about a lot in rendering: turning things, so rotation, moving things around, that's called translation, and scaling, making things bigger and smaller. Right? Those are very, very super common operations, and virtually everything you do with the stuff in a scene is some combination of those, and those are best represented as little 4x4 matrices. So since that stuff's already in there, you're able to take better advantage of it super cheap. Oh, and I ran out of words. Okay, so the moral of that story is, if we roll back and look at this V100, and there was a predecessor called the P100, which I think was the first NVIDIA graphics card that did this, used this half precision floating point and the 4x4 kernels and stuff, 4x4 matrix operations. But if you look at the numbers on this thing, it turns out that the reason you can get so much value, right, 8 times as fast to go from here to here, and the reason you, from here to here, the reason that it's so much faster is because all that stuff was already in there anyway to do the graphics. It's just now you're taking advantage of it because this specific kind of machine learning happens to be straightforward to express in a way that takes advantage of the hardware that's already there. Okay, and that's it. We're out of time. So next week is our last and final week. So we're super excited. It's May 1st, isn't it? Next week? May 1st, Tuesday, May 1st. It's our last one. It's very exciting, and you'll love it. So come back next week, and then that'll be it. You'll be the world's greatest expert on your own research, but now you'll know some HPC stuff too. All right, see you next week.